Welcome. Today we will explore the critical role of storage in AI infrastructure. We will examine why data throughput is a defining performance metric and how specialized architectures prevent bottlenecks in training workflows. Standard IT storage is often a static repository. In AI, storage is the fuel line for the compute engine. We organize this into a hierarchy to balance cost and speed. At the base, we have high-speed shared storage holding petabytes of training data. Above that, local NVMe provides fast caching on the node, capable of delivering over 55 gigabytes per second. Ideally, data flows seamlessly up this chain. If any link is too slow, create a bottleneck, leaving powerful GPUs waiting for data. Therefore, understanding this hierarchy is the first step in architecting for AI performance. This diagram illustrates the data flow hierarchy. At the bottom, massive datasets reside in shared storage. Data moves up to the local NVMe cache on the server, then into system RAM, and finally into the green GPU memory node where training occurs. The goal is to keep the data moving upward fast enough so the GPU never idles. Do we obsess over throughput? Because AI training is iterative. A model reads the same dataset multiple times, known as epochs. We need massive read bandwidth, often exceeding 40 gigabytes per second per node, to keep up. Unlike linear video streaming, AI workloads often involve small, random I/O patterns, such as loading thousands of individual images or audio files for processing. If storage throughput lags, experience GPU starvation, where the most expensive asset in your data center sits idle, waiting for data to arrive. Therefore, we optimize for aggregate file system performance and high peak node performance. This visual comparison demonstrates the impact of throughput on ROI. On the top path, low throughput from storage leads directly to GPU idle or starvation, resulting in wasted ROI because expensive hardware isn't working. On the bottom path, high throughput matches the GPU speed, leading to 100% GPU utilization and maximized ROI. To maintain this high throughput, we cannot have storage traffic fighting for bandwidth with compute traffic. In architectures like the DGX Super POD, we implement a dedicated storage fabric. This is a completely separate physical network, often built on InfiniBand or Spectrum-X Ethernet. It is distinct from the compute fabric used for GPU to GPU communication. Separation ensures that when a node pulls massive datasets from the storage array, it does not congest the high-speed internode communication required for model synchronization. This dedication is essential for predictable performance at scale. Here we see a single DGX node. Notice the split in connectivity. The top connections go to the compute switches for internode talk. Crucially, the bottom connections connect to a completely separate storage fabric, leading to the high-speed storage array. This physical isolation prevents traffic collisions. Finally, we optimize the data path itself using NVIDIA GPU Direct Storage, or GDS. In a traditional workflow, data moves from storage to the CPU, is copied to system memory, and only then moves to the GPU. This bounce buffer consumes CPU cycles and adds latency. GDS enables a direct path from local NVMe or remote storage directly into GPU memory via RDMA. Bypassing the CPU, we significantly increase effective bandwidth and reduce latency. This ensures that the storage subsystem feeds the GPUs as fast as the network allows, removing the CPU as a bottleneck entirely. This sequence diagram compares the two methods. The top section shows the traditional path, where data must hop from storage to CPU and system RAM before finally reaching GPU memory. The bottom section shows GPU direct storage, where data bypasses the middleman, going directly from storage to GPU memory via DMA or RDMA.